Okay. Now, the topic is integer programming, all right? This domain is a little bit different. The main idea is still the same. We still have our performance measure. We still have our environment. We still decide on decision variables. But this time, up until today, our decision variables are fractional, right? Amount or values, whatever. This time, like we did in the very beginning in the mid cartoon thingy, we're gonna have integer variables only, right? So integer program, it's a linear program plus the additional constraints that some or all of the variables must be integer values. Even if you have only one integer valued variable, you will still be in the integer programming domain because you will no longer be LP. We may also have binaries. Like, okay, in the mid cartoon thingy, our integer variables were variables 1, 2, 3, 4, 5. We also utilize these binary variables a lot. You're gonna see why actually, but sometimes this is like we either have it or not. And for those kind of situations, we define a variable that we say binary variable, right? Why do we have integer programs? Well, because that's more realistic. In real life, we usually need to have integer valued variables, but they're more challenging for formulating, and it's also more challenging to solve these problems, right? Just keep in mind, solving these is 303. In 202, we're gonna learn how to solve linear versions, but we're gonna learn how to model them too. All right. So remember the assumptions of linear programming: proportionality and additivity, divisibility and certainty. In the integer programs that we will have, the proportionality and additivity will remain, certainty will remain. We will only relax the divisibility assumption, okay? We will still have linear functions. We still need them. We will still know the environment with certainty, okay? If you don't know what's happening, if you're in a stochastic environment, you're in course 325, right? In 202 and 303, we're in deterministic environments, so we will still know the parameters for certain, but we will just relax the divisibility assumption. Okay. Examples. Bus scheduling. Let's look at this example then. All right. Municipality of Ankara, all right, is trying to find out the number of buses required for a certain line, okay? And depending on the frequencies and number of people and everything, they have clustered the time slot of a day in 6 periods. So from midnight to 4 a.m., 4 a.m. to the morning, then the very early morning slot, 8 a.m. to noon, afternoon slot, late afternoon, and evening, all right? And according to their whatever analysis, these are the number of buses required for each period, okay? So for midnight to 4 buses is enough. Then from 4 to 8, you require 8 buses, then 10, 7, 12, and 4, okay? This is the problem setting. Now, once a bus with the driver starts to work, they're supposed to work 8 consecutive periods. And then take the 16 hours off for a 24-hour day. Okay? This means when one guy starts in one period, this bus works in that period and the next period, and take the rest of the periods as off. Okay? And this is a 24-hour cycle. One cycle finishes, the other cycle starts. So today's last bus can also work for tomorrow's first bus, depending on its 8-hour slot. Okay? All right, our problem is, okay, how many buses do I need? What is the minimum number of buses so that I satisfy these requirements? Okay? Well, the next slide immediately tells you the decision variables, so I cannot make a discussion, but there are two options. First of all, well, yeah, the number of buses will be our variables, but what version of it? Because they work for 2 periods, okay? If they worked for only 1 period, I was okay, let xj denote the number of buses in period j, and then it will be a very easy problem. But my buses works for 2 consecutive periods, okay? So there are 2 options in here. Option A says number of buses working in period I. All right, yeah, maybe. But number B says number of buses starting to work in period I. If I define it like this in option B, my formulation is a lot easier than if I were to do it for part A. Here it comes. Alternative A, in alternative A, the bus that's working here, you don't know if it is its second period or first period, right? You need to deal with that, with either additional variables or putting in an index there. It is its second period or first period. It is doable, yes, because, by the way, there is not only one option to formulate a problem, right? Well, if I can come up with such an example, I might end up with 133 different models from each of you, right? There is no only one. There are good ones with less variables, easier type of constraints, and there are some more sophisticated ones. But as long as it works, as long as it's correct, it's okay, all right? So yes, part A can also be doable, but you need additional thingies there because you don't know when that bus started. But if you define your variables like B, the number of buses starting to work in period I, then it will be easier for us because that's what we're going to do. We're going to minimize from x1 to x6. Remember, we had 6 periods. So the number of buses working in a day are the number of buses started to work in that day, yeah? Those are individual buses. So I'm summing their minimum. Good. Now, the first constraint, x1 plus x6, let's go back. Now, the buses working in period 1 are the ones that started now, or the ones that started the last period of yesterday. So x1 plus x6 should be at least 4. That is for my period 1. For period 2, I need 8 buses. Who are working in period 2? The buses who start working in period 1 and the ones who start working in period 2. Their sum should be at least 8. 2 and 3 should give me 10 because that was the number of buses for that period. 4 and 5, 5 and 6. Yeah? If you define your variable like this, now I defined it saying that these are the number of buses that start working in period 1, in period 2. Then I know this is their first period. I don't need to make another distinction trying to figure out if they were already working or not. Yeah? Then this would be the model for the formulation. Clear? Yes?
The last one, 5 plus 6 is greater than 4, but shouldn't it be 12?
Let's see, x5 plus x6. These are the guys working in period 6. Yeah, it was 5 and 6. x5 and x6. So x5, number of buses started to work at 5. They will also work for period 6. So x5 and x6 are the buses working in period 6. And in period 6, I require 4 buses. So the formulation is correct. Right? Any other questions? Clear? All right. This is just saying you what I just said. This is number of buses. I can't have half a bus, 1/3 of a bus, right? So my number of buses definitely needs to be integer valued. That's why we write xi positive, non-negative, and integer, okay? Then I'm looking for integer valued x's so that these conditions are satisfied. Yes? Okay. Another example. Burger King. Number of kitchen employees this time. According to rules and whatever, the workers work for 6 days and take the 7th day off. All right? I know how many workers I require each day in total, and I want to make sure that I have as less, I want to do this with minimum number of workers. Yeah? I want to come up with a feasible schedule so that my kitchen is working with minimum number of workers. Again, the next slide already has the decision variable, but be careful. I'm not saying if the guy is working or not, because then I have to know what day it is. It is 3rd day, 4th day. That's tricky. But the guy is not working only 1 day. So let me define it as a variable. Let xi tells me number of workers who are not working that day. Then they will be working in the other 6 days. So x1 will determine number of workers who are not working on Monday. But then that will be the number of workers working on Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Yeah? So I don't need to make the distinction which day is this for this guy so that he's going to take the day off or not, right? So these are just, I'm trying to give you why we should be more careful in defining the variables in this domain. Yeah? Because the immediate variable would say, okay, number of workers working on the day. No. In that case, because number of workers working in Wednesday, I don't know if it is 5th day, 4th day. It requires a lot more additional variables. Doable, but requires additional thingies. But if I just say, okay, if x3 determines me number of workers who are not working on Wednesday, then those x3 are actually working on the other days. x2 can also work on the other days. Because x2 is only telling me number of workers who are not working on Tuesday. Then they're working in the rest of the days. Yeah? So we already defined the decision variable. I'm going to write the model. Yeah. It again wants to minimize the number of workers. So I will minimize x1 to x7. The one who's not working on Monday is my employee. That's his day off. So it is again another way of counting my total number of workers, right? Subject to. Now, Monday. The workers working on Monday are everybody but x1. Because x1 represents the workers for which Monday is the day off, right? So x2, 3, 7 should be at least 8. This is my Monday constraint. Tuesday, x1 plus, I'm not having x2 because Tuesday off, x3, x7 is at least 6. Wednesday, x1 plus x2, then I'm skipping x3 because that's their day off. x4, 7 is at least 7. Wednesday constraint. Thursday, 1, 2, 2, 3. I'm skipping 4, 5, 6 and 7 is at least what? This is Thursday, 6 again, yeah? Friday, x1 up to x4. I'm not having x5, that's their day off. 6 and 7 is at least 11. And finally, Sunday, everybody up until x6 should be 9. Then you're supposed to write xi positive and integer. Okay? Okay? Any questions? Just keep in mind, in these two examples I showed you, I tried to give you the challenge of defining the variable, all right? In the LPs, it was that easy, yeah? Or, I mean, it is also easy in these cases too. You just have to be thinking correctly so that which way would lead you to a cleaner, easier formulation, all right? Okay. Assignment problem. There are, yeah. Monday, Tuesday, Wednesday, Thursday, Fridays. Yeah, you're right. I missed one. Which one did I miss? Apparently, I missed Friday. Yeah, I missed Friday. Or I write Friday, but I written Saturday's thingy there. Yeah, thank you. This is actually 9, then plus Saturday constraint. Write that. My board is finished. Yep. I'm done with the boards. Okay? So you have to write a constraint for each day. All right. Assignment problem. Now, there are certain problems which appear a lot in many different domains that they have their own names and everything. Like, okay, workforce scheduling, production planning, yeah, but this is like assignment problem, and people jobs to carry out, right? And machines jobs, anything. So everybody can do one job, each job has to be done, okay? Each person is assigned to carry out exactly one job, and each job has to be done by exactly one person. You cannot assign 3 guys to do the same job if it is a one-person job. And the guy cannot perform 2 different tasks if he can only do one task at a time. Yeah? This type of problems are called assignment problems, and it's very well studied. It appears in many different domains. So the problem is find the assignment of persons to jobs so that total time is minimized, total cost is minimized, whatever your performance measure is, yeah? This is a binary variable. Remember, I was saying there are also certain cases that we only say 0 and 1, because now each person does only one job. So number of workers performing task I doesn't make sense. So the makes sense variable this time, if that person does that job or not. So my binary variable has 2 indices, x, I, j. If person I performs job j, that's a 1. Otherwise, that's a 0. All right? These are yes-no decisions, and for these types of situations, we define binary variables. Okay? I don't say number of workers doing it, doesn't make sense. It's either 1, well, it has to be 1. I just have to know who does it, right? So I have n people here with n jobs there. I just want to know who does that. That is the assignment problem. So I define a binary variable to represent the assignment for me. Yeah? And this is the formulation then. I want to minimize my total cost, time, whatever Cij is, my performance measure. And for the x's that I make the assignment, I'll take the cost. Now I have to make sure that each person can only do one job. So for each person, their summation over xij is 1. So x1, 1, 1, 2, 1, 3, 1, 4 equals to 1, because x1, 1 is 1 doing 1, 1, 2, 1 doing 2. So the guy 1, numbered 1, will only do one job. right? So this is actually doing it. Overall jobs for each person, only make one assignment. This is it. Make sure that each person performs one task. And the second constraint is doing the same thing, but this time fixing the job and summing over persons. This job can be done, so this is X, 1, 1, 2, 1, 3, 1, 4, 1. The second constraint, right? Task 1 has to be performed. And this, these Xij's are binary variables. Clear? This is really important. Defining binaries in the appropriate manner with correct indices is really crucial, right? And this was an example. This is a very typical example to define a binary variable. Who does what? Have you noticed something? Now, what happens if I have more jobs than my persons? Any ideas? Yeah? Which summation? The second one? But then, yeah, okay, there are ways to handle that, but the assignment problem works when the number of jobs and workers are the same to each other, exactly the same, so that nothing is left out. Yes, we can handle it with the dummies. We assign arbitrary persons with large costs and everything, but in the standard setting, you have to have number of jobs and workers equal to each other. If I have more jobs than my number of workers, the first thing you would say, well, it's infeasible. If you want all the jobs to be done, and if you don't have enough workers, your problem is infeasible. Then you have to ask your decision maker, give me something. Then the decision maker will say, okay, it's okay to left out some of them or whatever, right? Or if your workers are more, yeah, like you have 8 jobs and 12 workers. That means you're gonna leave 4 guys resting, if it's allowed. But in the standard setting, every person has to work 1 job, each job has to be done. If this is the case, and if my number of workers and my number of jobs are not equal to each other, then the problem is infeasible, yeah? Then you need to have additionals from your decision makers. Oh, yeah?
Is there a chance to load 2 guys for a job, but all the work have 2 workers?
You're defining another problem. In the original problem setting, I said each person can carry out 1 job only, and each job has to be done by 1 person only. Yeah, you're trying to come up with a way when the number of jobs and workers are not equal to each other. Yeah, well, yeah, but in that case, you have to go back and change your environment, if it's allowed. That's what I'm trying to say. All right, knapsack. This is, again, a very well-known, very well-studied problem, right? You're going on a trip, or every morning you're coming to class. My kid is literally going to school with a suitcase every day. I don't know what she's putting in there. But she has a huge, heavy bag. And for her, the capacity doesn't work. But anyway, so you have a knapsack with a capacity, B kilos, all right? And you have different items that you want to put into your bag, yeah? Every item has a weight and a utility for you, all right? If you carry that, it gives you something, whatever, right? So how would you pack your backpack so that your utility is maximized? What do you think the correct decision variable here is? Because this time it's empty. So is it an integer variable or a binary variable? Integer variable. We define xi Integer. Hold on. He said integer. Is it an integer variable or a binary variable? Binary. Because you're not going to put 3 calculus books in your backpack. It doesn't make sense. You either put your calculus book or not. Yeah? You don't put 3, whatever it is in your backpack. It's either you put that or not. Right? So it's a binary variable if item I is in the backpack. That's 1 or 0. Those are called binary. 0 otherwise. W means otherwise. As I said, it doesn't make sense to put 3 calculus books. You either put it or not. There is the integer variable version too. Like if you have 3 jackets, whatever. But the standard knapsack is if you put it there or not. These are only one of them. You only have one of those. And you're trying to figure out which ones to put in your backpack. It's a special integer problem. It's binary. Your variables can only be zeros or ones. You don't have 2, 3, 4. So it's a special integer program, yes. But we call it binary. Clear? Okay. We define the variable. Tell me the objective function. Tell me the objective function. What do we want to do? Let me remind you. Yes?
The total should be less than or equal to 15 kilograms. So
I'm asking the objective function. Let's start with the objective function. Yes? Sum. So we're going to maximize the summation over I from 1 to n, ci times xi. If I put it in my bag, I get the utility. If I don't get it. So you sum it over all possibilities, x1, x2, x3, whatever, how many you have. Subject to. What is my constraint? Now you can talk about your constraint if you're ready. Here it is. Yeah? You want to say it?
Summation AI xi smaller than b.
Sum over I, ai times xi, should be less than or equal to b, my total capacity. If I put the book in, it comes with the capacity of it. If I don't, it doesn't. Yeah? And never ever forget, xi's are binary for all I. Yes? Clear? Yes. AI was the weight of it. It's here. Yeah? B is the total capacity. So this B, AI, and CI, are they variables or parameters? Again, I want to hear the whole thing he's saying the same time. AI, BI, CI. Variables or parameters? Parameters. What is my variable? XI. Any questions? Yes.
Knapsack problem shouldn't necessarily be an integer programming program. It can be only programming as well. Since the programs can take fractional values.
But the book, kilos are, yes, but those are not my variables. The kilo of the book is my parameter. The book itself is integer. You can't carry half of your book. So what I'm deciding, that's a very good question. Which determines the problem being integer or not is not the parameters, but the variables. The weight of the book can be fractional, yeah, 2.5 kilos. But I put it or not, right? It's one book, so I cannot cut it. So the variable being integer or not, makes the problem IP or not. Clear? Any other question? All right. Workforce scheduling. Yes, but I think I need to clean my board for this. Okay, let's at least figure out and learn the problem. Maybe then we will have a break. Scheduling and production again, yeah? This time we're looking for a shoe company and we have the predicted demand for the next 4 months. 1, 2, 3, 4. Or months 1 to 4, the demand is 300, 500, 100, and 100. Okay. This gives our environment in here. What is the setting that I have to believe it? Each pair of shoes require 4 hours of labor and $5 worth of raw material. I'm producing, right? So for a pair of shoes, I need 4 hours of labor and $5 material. What else? Currently, I have 50 pairs in my inventory. So I have some stock that I could use, but next month I require 300, right? So at least this month I have to produce at least 250 so that I satisfy this month's demand. But I do have some in my inventory. What else? Now, in real life, we don't just produce for next month or for today, all right? We can do the production, give them in our inventory, and use from there. Think about Algida, for example, ice cream, yeah? Can you imagine that the Algida factory is actually producing for August's demand in August? No way, right? In that case, the factory should be shut down in January and December, but that's not the case. What happens is they produce for stock. And in August, they utilize what were already in the inventory. That is called inventory, okay? So that also works in other environments too. Not this much of seasonality. Not every product have this much of seasonality, but still we require it, right? So apparently we have 50 pairs of shoes in our stock. But there is a cost for holding it in the inventory. It's like tying up your money there. Sometimes it's running the inventory with people there. For Algida case, you need to have a freezing environment, blah, blah. There is a cost, right? In our case, then, if for each pair of shoes that is left in my inventory, I'm supposed to pay $30. All right? Currently, I have 3 workers, yeah? That I'm paying $1,500 per month for them. Each worker can work up to 160 hours each month. I can hire a worker and I can fire a worker, right? Because I have to satisfy my demand. So how to meet the demand with minimum total cost. Let's recap the problem. I'm producing shoes. I currently have only 3 workers, and they can only work up until 1,600 hours a week, month, and I do have demand to satisfy, all right? So how should I satisfy the demand with minimum total cost? I'm paying my workers, I'm paying my inventory, I can hire or fire workers because I need them to produce my shoes, right? And, like, for example, each pair of shoes require 4 hours of worker time, labor time, right? We need to come up with the best workforce scheduling. So we need to formulate a model that will give us this. Let's have a 10-minute break. We will continue in the next hour.